Matt is going to talk about number 23, and then Garrett has 36. So we're going to look at those two problems, and then as I said, we'll go over others that you have questions on. But we'll have Matt come up first. Anyone need a stapler passed around? Oh, sorry, Matt.
So I had 23, and the problem was 3 parentheses x minus 3 parentheses squared plus 2 equals 26. First you subtract the 2. So then first you subtract the 2 and from the 26, and then you get 3 parentheses x minus 3 squared
Yes.
equals 24.
I'll let him know.
Then you divide the 3 on both sides, and then you get x minus 3 parentheses squared equals 8. Then you square both sides to cancel out the squared, and then you get x minus 3 equals the square root of 8. So then you find the factors that equal 8 with a perfect square, and then you get 4 times 2. And then 4 is the square root of 4 is 2, so then you get x equals 3 plus or minus the 2.
Any questions for Matt? So you cannot combine them together any further because they're not considered like terms. So we have the 3, the plus or minus. Don't forget that plus or minus sign. Every single time you're solving for something that's squared now, and you're taking the square root, we'll have that plus or minus. And that accounts for the fact that there's 2 sides of a parabola. The axis of symmetry goes into between them, so you have to have that number on the left and the right of the axis of symmetry. So that's why that plus or minus is there. So 3 and then plus or minus 2 square roots of 2. Questions? So the other one Garrett has is the last one.
Okay. So I had 36. I had to find at what month the average operating cost was $1,430. So first I plugged 1,430 for the cost into the equation. I subtracted 550 from both sides. And next I divided by 0.55, and then I squared both t squared and 1,600 to get month 40.
Any questions for Garrett? So he plugged in the amount that you were looking for the cost, and then he solved for the t squared by trying to get it by itself, as if it were a t or an x. Just because it's squared doesn't mean the process is changing. So exactly as he said, he took the 550 to the other side, divided by 0.55, and then took the square root of both sides. Garrett, why doesn't that get a plus or minus with it? It has to be positive because you're talking about the number of months. So it is a positive value. It's 40 months. It doesn't get the negative there because months is like an actual obtainable thing. We don't get a negative number for the number of months. Any questions for 36? All right, so let's go back to the beginning and look at numbers 8 and 9. Then I want to talk maybe about the 20, one of the ones on the other side. 28. So looking at number 8, there's a couple different ways that you can kind of approach 8 and 9. It just kind of depends on what you're thinking about when you look at the problem. But number 8, we have the square root of 7/9 times the square root of 4/7. So one way you could think about this problem is by separating the 7 and the 9 into their own square roots. and the 4 and the 7 into its own square root. Because that's really what it means when you have a square root over the whole thing. You really have a square root on the top and a square root on the bottom. Can any of those parts be simplified? Julia? Yeah, the 9 and the 4. So we have the square root of 7 over 3, 2 over the square root of 7. So you can simplify the pieces that are perfect squares because we're taking the square root of them. So now we need to continue to simplify it a little further. Is there anything else that we can do to try and simplify this? So how else can we kind of like work through this problem? What does times mean? If you have two fractions and you're multiplying those together, what does that mean you're supposed to do with them? How do you multiply fractions together? Holly, what do you think? Yeah, and she's even using correct terms here. So numerator times numerator, denominator times denominator. Well, when you have a number outside and then a number inside, you don't physically multiply them together. They just get written next to each other. So the 2, and then it gets written next to the square root of 7. Because the 2 is outside, the square root is underneath. The 7 is underneath the square root. So really, you're just writing them next to each other. Same thing with the 3 times the square root of 7. We would just write it as 3 and then times the square root of 7 written next to each other. So Holly, what do you think would happen with those square roots of 7s? Yeah, they would eliminate. They would go away. They would cancel because the square root of 7 divided by the square root of 7 is 1. Just like 7 divided by 7 is 1. They're both the same root, square roots, so they cancel. And then you are left with 2 over 3. So we really didn't need to do any kind of rationalizing with that because the square roots ended up canceling out from the problem. So number 8, you should have 2/3. So if we look at number 9 and kind of think about it in a similar format. So we have the square root of 24 and then the square root of 80 over 192. Big square root there. So bigger numbers here. What do you think you could look at and try and do first since the numbers are so big? Emma, what do you think? What could you try and do first with this? What did you do first? Okay, and what did you get for that? Out of here? So if you divide, you're dividing it, reducing it by 8. And what did you get when you reduced it? 10 over what? 24? Okay, so she said she divided it by 8 and gives us 10 over 24. So Emma, what would you do next then? Okay. So I just broke them down so that they're in their separate square roots. And then Emma, what do you notice about this problem? So the square roots of 24 are going to cancel out because we have the square root of 24 times the square root of 10, and then on the bottom we have the square root of 24. So they cancel and you end up with the square root of 10. So that's one way, sorry you can't see that. This is one way that you could have kind of broken down the problem. That's just one way. There are multiple ways to reduce that, but that just is one way that it works nicely for you. But I would say if you have big numbers and they're even, like 80 and 1 over 192, reduce those numbers. See if they can break down. See if those numbers can become smaller values. And then that actually works out nicely again because those 24s will cancel for you. And you just get the square root of 10. That's just one way to reduce it, so it's not the only way. There are multiple ways to reduce that problem. You may have reduced it differently and still had the square root of 10, and that's fine. Questions? So I'd like to flip it over and look at one of the problems on the back. So 28, 30, and 32 say when an object is dropped, its height can be determined after t seconds by using the following object model. So we're talking about something just physically falling. So there's no arch to it, it's just being dropped from a building, being dropped from a tree, being dropped from, I don't know, a mountain, a cliff, like it's just literally being dropped, so it's falling down. So the falling object equation, or formula, is h equals negative 16t squared plus s. And it says s is the initial height where it starts. So if I drop my pen from the top of my arm, however high that is, that would be the initial height. It says we want to find the time that it takes to hit the ground when it's dropped from a height of whatever feet is given. So we have this object, whatever it happens to be, and it doesn't matter what kind of object it is. So it could be my pen, it could be a rock, it could be a stapler, anything, a book. We want to find out how long it takes for it to fall 160 feet. So the first one, we have 160. We have this formula, negative 16t squared. And then s, it says, is the initial height. That's its starting height. So if you want to think of s as being the starting height, it's starting at 160 feet. It's going to hit the ground. That's where it ends. That's that other value here, the h. That's where the rock or the pen or whatever it is that's falling is ending. If it's hitting the ground, what's the height of the ground? Holly? 0. So you're plugging a 0 in for this h here because that's where the location or the height of where it's ending at. So you have a starting height for s. The end height is wherever it's stopping, whatever it's hitting. In this case, it's hitting the ground, so we plug a 0 in there. If it says that you catch it, so I would drop it here and end up catching it maybe at 3 feet above the ground, then I plug a 3 in for that h. So whatever the end height is the value that goes in for the h there. So we have a negative 16t squared plus 160 because 160 is where it starts, the 0 is where it ends. And now we have to solve this little equation. So Will, what would you do to try and solve this equation for t squared?
Subtract 160.
Sure, let's take the 160 to the other side. We're trying to get t squared by itself, so we want to isolate it. You could take that 160 to the other side. And then what else would you do, Will?
Minus 16 from both sides.
And 160 divided by 16 is? Anyone help them out? Julia? 10, yeah. So 160 divided by 16 is 10. So Will, t squared is by itself, but we just want t, so we would
Square root both sides.
square root both sides. Now, if you left it as the square root of 10 seconds, because that's what we're solving for, t is in time, seconds, would it make sense for you to tell somebody, oh, it took it the square root of 10 seconds to hit the ground? No, it's a word problem. With word problems, this is when you want to have a decimal value. So, Will, can you give me like 2 decimal places? What is the square root of 10?
3.16 seconds.
3.16 seconds. So if an object falls 160 feet, it's going to take about 3.16 seconds to hit the ground. And again, like if we were catching it, if it was hitting the limb on a tree branch or a branch on a tree, then that h here would change depending on what the height is that it's starting at and ending at. So it starts at the s, it ends at the h, whatever that height is, whatever it's hitting. Are there other questions on the worksheet that I did not go over that you'd like to talk about? So if you look at number 5, there are 3 square roots in this problem. So we're multiplying 3 different things together. And I would suggest multiplying the numbers together first that are the same. So if it's underneath the square root, we can multiply that together. If it's outside the square root, then it stays outside the square root. So if you multiply 3 times 40 times, or 8 times 40 times 3. Anybody know what that is? 8 times 40 times 3? 960. Say it again. 960. And then this is the only number outside, so that's going to stay outside. And then on that sheet, the power sheet that I gave you yesterday, you're looking for one of those powers that you wrote down, like the perfect square, the number that you actually calculated to go in the 960. Maddie, did you find one? No. Does anybody have one? 64. So Rebecca said 64 times what, Rebecca? 15. So you're looking on the sheet, you're picking just the numbers on the sheet that you have written in your handwriting, not the ones that I typed. So 64 times 15 makes 960. Rebecca, the square root of 64 is 8. Rebecca, what do you do with this 3 that was sitting outside? So we don't add it to 8, we multiply it. And the reason we multiply it is because currently this is 3 times the square root of 960. They were all being multiplied initially. So when you take that number out of the square root, we're still going to multiply it together. So if we multiply these, we end up with 24 and then the square root of 15. Nice job, Rebecca. So multiply all the pieces together that are underneath the square root. The 3 that's outside remains outside. And then we can break that square root down using one of the numbers that's on the sheet there. Questions? So I'd like you to place your name on that worksheet and pass it forward, please. And then in your notes packet, if you'll turn to section 4-6. So today we're going to talk about something called a complex number, which really deals with the imaginary number. Does anybody know what an imaginary number is? How you find it, where it comes from? Julie.
It's a number that doesn't really exist, like if you have like a square root of negative 16, it doesn't really be like 4.
So he said it's a number that technically doesn't exist. No, it really kind of doesn't exist, but it happens when you take the square root, maybe, oh, there it goes, of a negative number. So in your calculator, when you plug in the square root of negative 16, it says error. Because it's not a real number, you can't take the square root of a negative value. So that negative part underneath the square root, there aren't two numbers that we can multiply together to make a negative value. So that's why the calculator says, hey, this doesn't work, this doesn't exist. However, people in math don't like when things don't work. So they continue to work through problems and see if they can find a solution or create something new so that you can continue to work through problems. And that is how the imaginary value, the imaginary unit, the imaginary number was created. So an imaginary unit is just the square root of negative 1. So the reason this was created was because a lot of problems, when you solve them, you end up getting negative numbers underneath the square root. And again, like some math person was like, hey, I don't like this, I don't like that we can just stop here, we need to go further with the problem. So the imaginary unit, the negative part is what creates the I. So when there's a negative underneath, we're going to pull that negative out and make it an I. I make mine with like a little curly tail on it, kind of italicize it. You can make yours however you want, but you'll see it as like kind of an italicized I. So when you pull that negative outside, then you have a whole number back underneath the square root, or a positive number back underneath the square root. Because that's when you can take a square root of a number when it's positive. So the negative part comes out and makes this imaginary value. And then you still have the square root number left. What is the square root of 1? Just 1, yeah. So this would just be equal to 1i, or we would just say that it's equal to I. There are 4 common powers of I that we'll talk about. I to the first is just I. I squared is the number -1. Because if you have I times I, you're taking the square root of -1 times the square root of -1. And when you multiply those two numbers together, you end up just getting -1. So I squared, when we have an I squared, it really is the number -1. I cubed is -I, and I to the fourth is a positive 1. Because I squared times I squared is -1 times -1. So these 4 values can be reduced. Any power of 1 through 4 can reduce to actual values. So an I, a -1, a -I, a positive 1. So these are like properties of I. We call it a property of I. So a complex number includes a real number and an imaginary number. That's what makes it a complex number. A is the real number, the I part is the imaginary number. So our answers will include a real and an imaginary number together, and that's called a complex number. So it's not just a real value, it's a little more complex because it has both pieces in it. And then the last definition here, we'll use what Julian gave us. So he said the square root of -16 is really I times the square root of positive 16. Or Julian, you said that would become 4, and then we have the I. So an imaginary number exists because a negative underneath the square root, that negative pulls out and becomes the I, so that then you can simplify the square root still. So we can simplify the square root of 16 because it's 4. But it has an I with it now because initially it had a -16 underneath the square root. Questions? So now, pretty much from this point on in math, if you have a negative number underneath the square root, we won't say it doesn't exist. We'll say that it just makes an I, and we can continue solving through the problem. So if you look underneath here, there are a couple of examples or properties. So it says if r is a positive real number, then the square root of -r would be equal to I times the square root of r. So that means the square root of -3 is equal to I times the square root of 3. It's just saying that you're pulling out the I separate, keeping the square root the positive then after you pull out that I. Number 2 says, by property number 1, it follows that I square root of r squared is -r. I want you to kind of think about that, look at that. So if we square these values, if we have I square root of 3 and it's squared, that squared goes to the square root of 3, that squared goes to the I, it goes to both of them. So that's really saying we have I squared and the square root of 3 squared. That's what that really means. So if both things are squared, it's really saying that both pieces inside are squared. Well, what happens if you have I squared? What's that equal to? Rebecca? -1. Rebecca, what happens if you have the square root of 3 squared? It cancels and it just becomes? Yeah. So that's just equal to a -3. That's what we did yesterday. We squared and had square roots. They cancel. They undo each other. So -1 times 3 is just equal to -3. It's weird, it's different. So I think there are 2 equations underneath that it wants us to solve. So thinking about what you did yesterday, we're still doing the same thing, except we might end up with an imaginary number. We have 2x squared plus 15 equals -35. So Garrett, what would you do first to solve for x squared? Yeah, let's subtract 15. And then Garrett, what else do we do? Divide by 2. What is -50 divided by 2, Garrett? Yeah, -25. All right, Garrett, the last thing we have to do here. Okay, so because we want to get rid of the x squared, the squared and the square root cancel, leaving us with x. And then if I have the square root of -25, that's really saying we have I and the square root of +25. Garrett, what is the square root of 25? 5. So we have 5 and then I. Except because we were solving for x squared, what goes in front of the 5 and the I? So a plus or minus has to go in front of 5i. And that's because we were solving for x squared. So now anytime you have an x squared equation, your answer has a plus or minus in it. So x equals plus or minus 5i, both positive and negative. See if you can solve the next one while I try and get my MacBook to like me. Just go like this. So the second one, we would subtract 13. Mackenzie Myers, what else do we do after we subtract 13?
You can divide by 3.
Divide by 3. We're going to keep that as 10/3 and not write it as a decimal. No I in this problem because it's not negative. So Mackenzie, what will we do next?
You have to find the square root.
Yep, find the square root. So really this is saying we have the square root of 10 and the square root of 3. Plus or minus in front because we're solving for x squared. What do you do when you have a square root in the denominator? Oh, you don't have to know what it's called.
Rationalize.
Yeah, very good. That's good. You looked it up quick. What do you do to rationalize it?
You do the square root on the bottom.
Excellent. So whatever square root's on the bottom, we want to multiply by it so that we get rid of that square root on the bottom. So that's called rationalizing the denominator, taking the square root out of the denominator so that it's no longer there, because the square root isn't supposed to be in the denominator. We consider it unsimplified. So then Mackenzie, on the top, when you take the square root of 10 times the square root of 3, we get the square root of 30. And on the bottom, when you multiply the square root of 3 times the square root of 3, you get?
It would be the square root of 9/7.
Excellent. So it would become the square root of 9, but that's just 3. So that's rationalizing the denominator. So the square root of 10, the square root of 3 is the square root of 30. The square root of 3 times the square root of 3 is the square root of 9, but that is the whole number of 3. And that's what we want to have in the denominator of a fraction. Can you break down the square root of 30 at all? Is there a perfect square that goes into it? No. So this would be our answer for x. Not as nice as the answer for a, because we have a square root in this one, where a we have plus or minus 5i. Questions? So at the top of the next page, we're going to try and see if we can add and subtract complex numbers. So to add or subtract two complex numbers, it says add or subtract their real parts. So we're going to add the real parts together and their imaginary parts. So it's kind of like having like terms. When you have an x plus an x gets combined together. A 5 plus a 4 gets combined together. So imaginary numbers work like x's. It's not truly a variable because it's a number. But when you add things together, you have to add like terms. When you subtract things, you have to subtract like terms. So that's what these two things are saying here. If we have complex numbers and we're trying to add them together, we're going to add the real pieces and the imaginary pieces together. So if you look at example 2, it wants you to write the complex number in standard form. That just means you should have a real number and an imaginary number combined together. So we have 6 plus 3i minus the quantity 4 minus I. And I'm going to forego this step here, and I'm going to write it on the other side. So if there's a negative in front of parentheses, Gavin, what do you usually do when there's a negative in front of parentheses? Yeah, multiply it by negative 1. So this gives us 6 plus 3i minus 4, and then a negative times a negative makes a positive I, and that is an I back there. So Gavin, if we're supposed to combine the real parts together and the imaginary parts together, what would we add together here?
6 minus 4.
Right, so 6 minus 4, and he said 3i plus I. So 6 minus 4, Gavin, is? And then 3i plus I makes 4i. And that's it. This is standard form because you have your real and then your imaginary. The real number is more important. It gets to go first. That's what standard form is, so placing the real number first. So if you look at letter B, this says we're doing addition, complex addition. It doesn't have to be complex or hard. Just make sure you're adding the correct pieces together. So 2 plus 5i, you can get rid of those parentheses. That's just showing you where you have two separate complex numbers. Plus 7 minus 2i. So Julian, what would we get when you add the like terms together?
So you have 9 plus 3.
Good, 9 plus 3i. So 2 and 7 are the real pieces. The imaginary piece is 5 minus 2i. Any questions? So it's like a variable. You can pretend it's a variable because it kind of has the same properties as a variable. All right, looking at example 3 here. It wants us to multiply these together. So we have 2 plus I, negative 5 plus 2i. How do you think you'd multiply that? Should look really similar to something that we multiplied at the beginning. Holly? Yeah, we FOIL this. It's okay that it's an I and it's not an X. We're going to FOIL this. So we're going to use the FOIL process. Pretend it's an X. So Holly, if we FOIL this, 2 times negative 5 makes 2 times 2i is, yeah, just like 2 times 2x would be 4x. And then Holly, I times negative 5 And then I times 2I. Nice job, 2I squared. If that was x times x, it would be x squared. So I times I makes I squared. Alright, so now we need to combine things together. So Holly, if we combine our i's together in the middle, we have 4i minus 5i. So what's that make? Right, negative I. And then is there anything else that we can simplify or change? That last piece says plus 2i squared. Julian?
I squared into -1.
Right, this is the part that can be simplified. I squared is really the number -1. So if there's an I squared in the problem, we can change that to be -1. So we really have -10 minus I and then -2. Because 2I squared is really a -2. So combining our real numbers gives us -12 and then minus I. So if you look at the 3 problems underneath, it just says to write it in standard form. So that means you're combining the real pieces and the imaginary pieces together. Be careful with that negative sign. Make sure you're distributing it through the parentheses. So for the first one, you would have -4 and then minus I. So 12 minus 16, 2I minus 3I. Letter B, it's the distributive property. So when it's a number in front, you distribute it through the parentheses. -4I times 9 is -36I. -4I times 5I is -20I squared. Kushal, is there anything we can do to simplify that problem any further? Yeah, so this piece back here is saying we have -20 times -1. So Kushal, how would you write that answer?
20 minus 36i.
Nice, 20 minus 36i. And then the last one, getting those real parts, combining them together is -2. The imaginary parts make 7 and I. So an imaginary number is created because there's a negative underneath the square root. However, it kind of holds the same property as an x. Your homework is in the book this evening. So page 279, 282. Tomorrow we're going to do a review day. So reviewing solving equations for x squared, reviewing complex numbers. Those two combined together. So you'll have a little review worksheet, a short review worksheet tomorrow.